When we look at mass spec, you really have what is on this page is pretty much it. Okay, your textbook goes through, I think, a little bit more detail behind it, but this is pretty much all you're looking for. And there are some names that pop out of it, common things that get referenced. The M plus peak is the peak, and we've listed this, the peak furthest to the right, but then the tallest peak within 3 units of the one furthest to the right. Right? There really isn't a better way to describe that. That's just the way it is. Okay? What that represents is that in the process of ionizing the molecule or blowing it up into tiny little pieces, all you've done is removed a single electron from your molecule. Without a single electron, your compound is now positively charged, and the mass has not changed. So mass spec gets you the molecular weight of your compound. Pretty handy. After that, you can start to do some analysis of what you can find. If the M plus peak is odd, then nitrogen is present. This has to do with its bonding structure with only 3 bonds. If the M plus 2 peak is the same height as the M plus, bromine's present. So the M plus 2 just means you've added 2 to that tallest peak. Why is this peak existing? What is the M plus 2? What does mass spec show you? The mass of the molecule, right? And it's going to be the mass of just a random average sample of an individual molecule. Well, if you look at a random average section or cross-section of an individual type of molecule, you're looking at a random cross-section of the type of atoms that went into the molecule, which means you do have an isotope effect. For hydrogen and carbon, 99% of hydrogen and carbon are hydrogen 1 and carbon 12. So we really don't see much of an isotope effect for some of our elements. Some jump out. Bromine is one of those some. Okay. There are 2 almost equal isotopes for bromine. Those 2 isotopes are 79 and 81. Of course, a difference of 2. Okay. When you average that, you then get the molecular weight that's shown on your periodic table, which is your 79.9. Roughly the average of 79 and 81. Okay? Because there's those 2 common isotopes, in a random collection of our sample or our molecule, if bromine is present, we see those 2 peaks being relatively the same height. Okay? Depending on the stability of the structure, I may have to hand draw in those 2 peaks, in which case they will look completely identical. If I don't have to hand draw them, they'll be close to each other, but probably not perfect. Right? And that's because it's not a perfect divide between them. We run into a similar situation with chlorine. Chlorine has 2 common isotopes. Those are 35 and 37. Since I got colors, we might as well use them. So our isotopes for chlorine are chlorine 35 and chlorine 37. For bromine, it was 79 and 81. Okay. Last thing you could potentially pick up, which is super, super rare, but every once in a while it shows up. If you have a peak at 127 that's corresponding to iodine, the other thing you can look for is a massive, massive, massive molecular weight. Okay, so you're looking at something over 200, potentially getting up to the 300 range. Iodine's probably present in your molecule. Okay. And it's just going to be that massive because iodine is really, really heavy. Okay. After that, I pretty much leave mass spec alone. Okay? And I don't bother to deal with it anymore because I don't think the input time that I have to go through for it is really all that value added because I can pick up other information elsewhere. Okay? But we're going to take a look at a couple other options. So if we look at an actual mass spec, first thing we want to go through and do, identify our M plus peak, because that gets us the molecular weight of our compound. Where's the M plus peak? 86. So it's this tiny little peak right there. You'll notice that most commonly that number is provided to you so you don't have to read it off the chart. Okay? That also happens to be the tallest peak within 3 units. What do we mean by 3 units? 3 to the left, 3 to the right. So between 89 and 83, there's really only 2 peaks present. One at 86 and one at 85. 86 happens to be tallest. There's my M plus peak. Okay. After that, you'll notice there's a bunch of other peaks showing up. What are all those other peaks? Okay, it's the fragmentation pattern for the molecule. Remember, what we're doing is we're blowing up the molecule on a bunch of tiny little pieces. And so our detector is just going to count to see what pieces hit it. So you notice that we see these peaks every so often. In other places, we don't see anything. Okay, why? Because no compound of that molecular weight, or no piece of that molecular weight, came through. Why is that 43 one so tall? .43 is smaller than 86, so I don't quite accept that it's big. It's a high abundance. That happens to be the most stable piece. So when we break this molecule apart, there's some piece that weighs 43 that is incredibly stable. That's why that peak is tall. I believe it's actually referred to as the base peak. Right? If you're really advanced at spec or at mass spec, what you can do is look at each of those pieces, predict what is the most likely piece they are, and then reassemble your compound to get you the final structure or your starting structure. Right? It requires practice and a decent amount of understanding of stability of ions and all that fun stuff. Up to you. If you want to go through and spend the time to understand those pieces, feel free to go ahead and do so. It's not required of the course. Okay, but it is kind of fun, and it can be a useful tool if you're moving into any kind of analytical chemistry. Right? So the next thing that we could go through and do, we have a molecular weight of 86. What does that mean? Not bromine yet. No nitrogen, because 86 is even. Why no bromine?
Because it's 79 or 81, and you would be left with 5 or 7 hydrogen.
Fair answer. I didn't come to that conclusion. At a mass of 86, bromine is either 79 or 81. So if there was a single bromine atom present, how many hydrogens or what other atoms would need to be present? The only thing you'd have left would be hydrogens, and we'd have to bond 5 or 6 hydrogens to a single bromine. Well, we can't do that. So that doesn't make sense. There's another reason that I was aiming for the bromine, but good job on the math. You would need to look for an M plus 2 peak. We would need to see a peak of equal intensity at 88. Is there anything there? Nope. No bromine. What does that also mean? No bromine, no chlorine. And no iodine. For what reason? It's too small. Okay. At this point, I personally would move on. Okay, on a complete solve. When it comes to multiple choice, I would use that information and see what I could find. Okay. There is one extra step that we could go through and do. What's that one extra step? What was that? We could try and come up with a formula, which could be very helpful on a straight multiple choice for mass spec. So what do? Take our weight. Why do we divide by carbon?
So we can get the number of carbons.
Why would there be carbons present? It's organic chemistry. So we can go through, take our mass of 86, divide by 12, and get, I'm horrible with my multiples, 72, so what is it, 6 and change? 6 point some numbers, which means we likely have 6 carbons, which gets us to a total mass of 72, right? Okay. What happened to that other mass? That difference is now our hydrogens, which is, I don't know my multiples. It says 7 and change. Man, who's got a calculator?
Only in organic chemistry.
I will adjust that in a second. So 84. Fix the math. There we go. So we'd come up with a possible formula of C7H2. Everybody okay with that part so far? Okay, why are you saying no? So are we okay with the math getting to this point? That's what we need to fix. Yeah. Okay. So we've got 7 carbons, 2 hydrogens. Okay. That matches the formula. That matches the mass. Everything about that says that is a possible formula.
Except for the bonds.
Is it a likely formula? No. Okay. So while this is still possible, it is a highly unlikely structure. So what do we do?
Go one less customer.
What we can do, since we have no evidence of any other atom being present except for carbon-hydrogen, we'll subtract 1 carbon. So we've got C6. And then we have to account for the mass of that carbon, so we add 12 more hydrogens, and we get C6H14. This is now a more likely structure. Could we remove another carbon? Theoretically, why not? We'd end up with C5H26. Is that a possible structure?
Yes.
Hearing some yeses and nos. For the no's, why are you saying no?
The max would be 2 times carbon plus.
If you remember your degrees of unsaturation, a fully saturated alkane is CnH2n plus 2. If n is 5, the maximum number of hydrogens I can get would be 12. I cannot physically put 26 hydrogens around this structure. Okay. We could still go through and subtract more carbons, but we've already reached our limit. There's no point in subtracting anymore. So I now have the most likely possible formula. Given that, I can now go back into my multiple choice answers and see if maybe we were being obnoxious and didn't give you just a bunch of halogens in it or something like that. Okay? Questions? So, 5 minutes you went through and did 1 problem. That's why I don't like going through and calculating the formulas. Because in 10 seconds I knew I didn't have bromine, chlorine, iodine, I knew the molecular weight, and I can move on. Okay? Questions? Yes?
Is there any other method of finding the formula? Because on the smart working, I tried to use this and
There is another method that looks at the intensity of the signals. You'll have to reference the textbook for that exact detail. I've never used that method, and I don't see that being remotely useful.
use this one. I didn't know how to determine the intensity of the synthetic intensity of the
Yeah, it goes based off of the intensities, which should be given to you. So I've seen some questions that give it to you directly. I'm not going to ask that on the test, and it shouldn't have made it into the homework. So if you talk to me after class, let me know where, and I'll actually delete that question from the homework, because there's no point in making you go through and do that. Other questions?
So would that, would it, if like it wanted the formula, would it give us like 2-methylpentane, or would it say C6H14?
As a possible answer, so if we asked what was a possible formula for this, there's 2 ways we could do it. You could see C6H14. You could also be given the structure. If you're given the structure, though, more than likely what's happening? We're going to change it. Okay? So for this one, what we could potentially do, you'd probably have to do it, be a little bit more careful on this. Throw in a we already said bromine was horrible, so let's not do bromine. Put chlorine, because that at least has a chance of coming out close to the mass. Might even have one, like that. Maybe throw in an OH. Okay. We'd have our 2-methylpentane. How many carbons we got? There's 2, 3, and I don't know. How about a benzene? You get something like that. Okay. Theoretically, all 4 of your answer choices. That's a bad one. Let me put on an iodine. All 4 of your answer choices would come up to the exact same molecular weight. Okay. More than likely, just because of how the test seems to work, one of them will make completely no sense. Iodine makes absolutely no sense, so you could eliminate that answer right off the bat. But the last 3 choices almost always will add up to exactly 86. So how would you eliminate the other choices? Well, the chlorine we could eliminate because it doesn't have the right thing. How would we eliminate the OH? we'd be given some other information. Maybe in a sentence it says there is no peak at 3300 in the IR. Well, that's an OH, so that can't be right. Okay, so you'll be given some information that would allow you to eliminate those answer choices.
Is there ever,
Sorry, just a sec.
I was just gonna say, so the M43 or negative 43P,
Mhm.
how do we use that other than saying there's a high abundance of?
What you would do is you would evaluate what structure would make up that 43 piece. Okay. Then what you can do is say, okay, now that I know this is a possible piece, and I know the possible piece at 57 and the possible piece at 71, you can then put those pieces together to get a starting structure. It is referred to as your fragmentation pattern. Okay. There are some kind of neat patterns that come out of that. It's not worth spending more time than what we've just talked about.
So, I mean, we don't need to do anything.
You don't need to do anything with it.
Useful for, I guess, getting the formula and stuff.
Nope. Well, it is useful for getting to the formula. Is it something that's useful for you to get to the formula? No, because you're not expected to understand how to get to it from there. What I'm doing is letting you know that you can find information there. And if you want to spend the time on your own outside of class, absolutely, I will help you do that.
so there's never with chlorine, because you have it as an example, and there's no M plus?
There's no M+2.
So
Can't have
there's
chlorine.
always an M+2 with chlorine.
Yes. You'll see that 1, 3.
So if you have an M+2 that is like 2/3 or so, like, how would you classify that? Would that be more considered a bromine, or would that be more considered a chlorine?
I will tell you that it comes out cleanly each time. The only reason it doesn't come out cleanly and get you that 1-to-1 or that 1 to 1/3 is because you've messed with the isotope effect. You're not looking at an average sample. So if I went through and said, I took this sample, I know it has chlorine on it, but I made sure there was no chlorine 37, I wouldn't see the M+2 peak because there's no chlorine 37. Okay? So I can invent a question to be stupidly hard to remove that M+2 peak. We don't need to invent a question. Is that another question? Okay. So yeah, you should get a nice clean 1-to-1 ratio or a 1 to 1/3. Okay. Easily within comparisons. If you see something other than that in the homework, let me know and I'll take a look at it. That's the only other place I could see you seeing that. Okay, other questions? Oh, we could look at more. Let's not look at that. So, NMR. And we just talked about mass spec. So this is really just your carbon NMR and HNMR now, because we've already finished mass spec in chapter 16. What's happening in NMR is you take a really, really big magnet and you use that really big magnet to look at the magnetic effects of each of your nuclei. So a nucleus has a magnetic, potentially has a magnetic moment associated with it. So what happens if you bring that magnet near another magnet? Do they have an effect on each other? Yeah, we can detect that effect. Okay, so that's the intent of the instrument. There are certain nuclei that are active for magnetic moments. Hydrogen happens to be one of them. Carbon-13 happens to be the other. Why, or one of the others. Why is carbon-13 kind of an odd one? What's the most, common isotope for carbon? 12. Why is it problematic that carbon-13?
There's an extra proton.
It's an extra neutron, but why is that potentially problematic for carbon NMR analysis?
It changes the positive ratio.
In an individual sample, the only one that NMR can detect is carbon-13. In an individual sample, how much carbon-13 is there? Virtually nothing. So if we look at the two spectra, HNMR is run usually very quickly. You can usually get a complete spectra in under a couple minutes. Carbon NMR, you usually need a couple hours because you have to build enough signal to noise to actually get a reasonable result out of it. Okay, so the HNMR tends to be used much more commonly and quicker and easier as an analytical tool. Carbon NMR a little bit less so just because its magnetic isotope is not in high abundance. Okay, there are other isotopes that have magnetic moments or other elements, we aren't concerned about those because they're not organic, okay? Or at least not organic enough for us to jump in here.
What makes carbon-13 magnetic versus carbon?
It has to do with the balance of the neutrons in charge in the nucleus. Okay. So you have to have the proper ratio to generate that magnetic moment. Without that ratio, it doesn't work. Okay. Actually, before we do that, so we've got our tiny magnets that we drop into a big magnet. Okay. What things could we potentially do? Well, we have to now tweak it somehow. That tweaking process is using radio frequencies. So we can change the energy of the radio frequency to now change what atoms we're potentially hitting, okay, or interacting with. And what we can do is monitor that time lapse between those, which gives us some information, because that radio frequency has to be able to make it into the magnet, okay, or into our tiny little atoms. So if there's a bunch of stuff in the way, we have to use a stronger and stronger radio frequency. Okay. Well, what stuff could possibly get in the way? Electrons. So the more electrons there are around our tiny little magnets of our hydrogens, the more shielded they become, and we end up seeing a shift, okay, on the energy necessary to cause them to be excited. Okay, so we can predict something about where our hydrogens or our carbons are located, okay, based on how far it shifts from some 0 point. Okay? So that's our electrons hiding and affecting our nuclei. Okay, the other thing that we could go through and do is realize that every hydrogen is a magnet. Well, if they're all magnetic and they have identical chemical environments, what should happen? Not even repel. If I take two magnets and I put them into the exact same situation, say one of them takes 500 hertz radio frequency, what is the other one going to take? The exact same. Which means what happens in the result? They're going to be the exact same signal. Right? So I wouldn't necessarily be able to tell apart from them from each other in our spectra. But what we can use with that information is look at the intensity. Right? Because if I have more magnets in that area, it's going to absorb more of that energy. So the intensity of my signal now changes. Okay, so we can start to evaluate how we can see just a chemical environment. We can also look at how many of those hydrogens are present. Next aspect. I take a small magnet and I put it near another small magnet. Do those two small magnets see each other? Potentially. What if I spread them apart? Not so much. So there's going to be some certain distance where those small magnets start to interact with each other. Much like our neighbors. The people living next to us we have some type of interaction with. But the people living down the block we don't really see very often, so we don't interact with them. So we can now start to see how each of the tiny magnets can affect each other within the larger magnetic field. Okay, so we get this neighboring effect as well. So what we've just pretty much discussed is pretty much the four main aspects of hydrogen NMR. You get how many signals do you end up seeing? You get a chemical shift, you get an integration, and you get a splitting pattern or multiplicity. So when we break down evaluating spectra, that's what you're looking at. One of those four things, right, which you should be kind of happy about. Because if you understand how many signals you've got, you now have a question answered. If you know something about the chemical shifts, you now have another question answered. Right? You know something about the integration, there's another question answered. If you decide splitting is way too hard and you don't even want to look at it, you just got 75% on arguably the hardest section of the exam. That's pretty solid. Okay? So divide your time accordingly to make sure that you can understand each of those individual aspects. So we've got kind of a symbol or a drawing, I guess, for this. We take our sample, we put it into a large magnet. We wrap it around some coils, which gives us something with our detector. We have an ability to control the magnet, and then we also have a way to send radio frequencies into it. And our detector changes or notices the energies or the radio frequency signals so that it can then output some kind of peak for us to then interpret. Based off all that information, what we end up with is just a nice simple plot that is our NMR spectra. Okay. This happens to be a nice instrument or image of one of the larger ones. The spectrometer is actually this guy right here. Okay. That's the instrument itself, followed by all of this computer software to actually maintain and make sure it runs appropriately. Okay. And to use it, you'd be sitting at this nice little desk here, hopefully punching a very few buttons and hopefully not breaking it. Okay. ASU, so 850 is the strength of the magnet in megahertz. ASU, I think, has a 900, and they might have even cleared 1,000 megateslas, I think, as far as strength. Their instrument is massive. Right? These things all rely on supercooled magnets to work. How do you supercool a magnet? Really cold liquid helium and liquid nitrogen. What's fun about that is you pour one into the wrong socket, it solidifies, because nitrogen will solidify before helium does, and you can freeze the whole instrument, and then you take in something that's probably a multi-million-dollar piece of equipment and turned it into a bomb, which is kind of funny, as long as you weren't the one that did it. Happened at ASU during a summer a couple years ago, and that was an interesting day.
Did you do it?
I did not do it. I just happened to be nearby. So this happens to be one of the larger instruments. The smaller ones, there's another image of one in the background. Usually the 300 or 400 megahertz. I think the 4 or 5 is probably about 7 feet tall. And you have to climb up a ladder and drop your little sample in. And your sample is just a tiny little tube. I'm going to steal your drink. A little bit smaller than the size of a straw. Okay, is where you would put your sample into that massive instrument. Okay, so kind of a neat little instrument to play around with. If you move to ASU, there is a researcher there that runs this instrument who really likes undergrads doing research in his work. So if you're interested in that, you should talk to him. So standards. One of the things we talked about is more or less shielded or de-shielded. That's in reference to how many electrons are around our hydrogens. The more electrons we have, the more shielded they are. The less electrons around it, the more shielded they are. And our signal shifts. It shifts from what? It's all relative. So if we don't have something to compare to, we don't have a way to interpret any of this. So that shielding or that reference is typically TMS, tetramethylsilane. So it's usually put in small concentrations, and that is our zero. Okay, so that is our zero signal. So you might see a peak at 0. That peak is not due to your sample. That's due to TMS. Okay, that's our 0 point. So all of our organic protons will absorb downfield of that. Okay. Be kind of aware you've got downfield, shielded, de-shielded, upfield, all of those terms I'm very bad with. I usually say bigger numbers or smaller numbers. Okay. It's good enough. Downfield and de-shielded, I'm like 90% certain are the same thing. Okay. Which is bigger numbers. Okay. So just kind of be aware of that. You may need to make sure you reference and get that straight. Okay. One of the things that has to happen in this process is our sample must tumble and move. Why must it move around? It's an interesting question. You guys will now all be a detector and I will be the sample. Okay, so if you detect me, you see me now, right? But if I now turn around, does the detection change? It does change. The viewpoint from the instrument now thinks, oh, that's a different structure. I'm now looking at the back of the structure. It doesn't have the processing ability to see that. So what ends up having to happen is our molecule has to freely tumble and move. Okay? This allows for us to actually average out those weird kind of inconsistencies with the structure, chair flips, right? So that we get a nice clean signal out of this. Why does this become problematic? Well, if it must move, what phase can we never detect or test? Solids would now be impossible to test in an NMR because they don't tumble and move. Okay, so what we end up doing is introducing another molecule. That other molecule is chloroform or dimethyl sulfoxide. Why is that now an issue? You're adding what? We can be as crude as something else. That's fine. We're adding something else. And in particular, that something else we're adding is another organic molecule containing both carbon and hydrogen. And we're adding it in massive quantities. When we're looking at an NMR, we can probably get away with about as much sample as we would use on a TLC plate. Right? So a very, very tiny amount. To get it into solution, we have to fill up that whole straw. So there is now a ton of chloroform and dimethyl sulfoxide relative to your compound. So what we have to do is come up with some way to remove that signal. The way we remove that signal is by removing the hydrogen and the carbon. But how can we remove the carbon and the hydrogen? What we do is change them to a different isotope. Hydrogen is active in the NMR. Deuterium is not. Well, what's the difference between hydrogen and deuterium? A neutron. That additional neutron changes the magnetic moment. It makes deuterium now invisible to the NMR spectrum. So what we end up using is deuterated solvents. So you may see the term CdCl3 because the formula for chloroform is CHCl3, but we don't want hydrogen. So we put in a deuterium. Right? The issue with that is that while deuterium is invisible, there's lots of water in the atmosphere with lots of hydrogen available to it. As soon as we open the deuterated solvent, what gets into it? Water and ultimately hydrogen, which exchanges with the deuterium, and we end up seeing chloroform again with that hydrogen. So depending on how clean your sample is, you may very well see another signal pop up. Okay? Chloroform in HNMR shows up at 7.26 as a clean singlet because there are no neighbors. In carbon NMR, it shows up as a triplet at 77.2. Right? Again, depending on the spectra that you're looking at, if it's completely synthetic, you won't see those peaks. Right? If it is a real spectrum, you will see those peaks show up. Chloroform happens to be the most common. The other one is dimethyl sulfoxide. Why do we call it D6 dimethyl sulfoxide? But why 6? There's 6 hydrogens in dimethyl sulfoxide. We have to replace all 6 with deuterium. Okay? And you again see a slightly different signal show up in your HNMR and your carbon NMR. Okay? So be aware those can show up. If you look at the spectroscopy packet, the ones labeled A, B, C are all real spectra. So the IR was taken off of an instrument at ASU. The HNMR and the carbon NMR were also taken off of an instrument at ASU. Okay, that was during the summer where they had that minor meltdown. Okay, so big things to get from NMR. Order of difficulty. Right? Top, number of signals. How many signals do you see? Right, the number of signals now tells you how many different types of hydrogen or carbon you have. So that's kind of a nice system. We can get it if we look at hydrogen NMR and we see 5 signals. Well, we got 5 different types of hydrogen. Remember, it's a type, not the amount. Right? Because it could be the same type showing up in multiple, or have lots of symmetry. All of those signals are going to show up at the exact same chemical shift. All we'd see is one signal. Okay? So it gives us the number of unique hydrogens and carbons. After that, you can get to the chemical shift, which is your rough local environment for both hydrogen and carbon. Okay, so if you're looking at hydrogen NMR, that's roughly in the range of 0 to 14. Okay, so our hydrogen NMR usually runs in the 14 to 0 ppm range. Carbon NMR usually runs maybe 220 down to 0. Okay. That gives us some information about what is around the hydrogen or carbon. Okay. After that, we can move into integration. The hardest part with the integration is realizing that this is a ratio, not an exact number of hydrogens. Okay. You'll notice that it also has now changed. This says hydrogen, it says nothing about carbon. Why? Because when we look at carbon NMR, if we tried to evaluate how many signals show up, what was our chemical shift range for carbon NMR? 220 to 0. What is included in that range? Your hydrogen signal. So what ends up happening when we move up to integration is that the hydrogen signal can affect the carbon signal. If that affects it, it complicates our spectra. So we can change how we interpret our carbon NMR to get different information about the hydrogens. But when we look at integration, we will only use hydrogen NMR, because in hydrogen NMR, the carbons don't affect. They show up too far downfield, we don't have to worry about them. Okay, so only in hydrogen NMR. And remember the ratio. Theoretically, if everything is nice and there's very little symmetry, you can add the ratio together and you would get the number of hydrogens in your sample. Okay, the perfect amount. Okay, but again, remember, this is theoretical. You're looking at a sample that has maybe 1,000 different molecules in it. Every single hydrogen in that 1,000 sample molecule gets counted by the instrument. Okay? So you can only pick up the ratio of them, not the exact amount. Last thing, everybody tends to panic about multiplicity. You'll hear me refer to it as splitting, because when I learned about it, we always referred to it as splitting. Multiplicity is a better way to look at it. This implies the number of different hydrogen neighbors. And again, comes back to hydrogen. If you look at special carbon spectra, you can see a splitting effect as well with them. I'll leave you to read the textbook on it if you want. I'm not going to ask you about that version of spectra this semester. Okay? So the splitting part is absolutely the hardest part. Okay? Once you've done all of that, it's now just a question of interpreting it and putting it all together. As simple as that. Okay? The best way for me to describe it is with all of this spectral information, is you are taking a puzzle and you are building the puzzle pieces. Once the pieces have been put together, then you can put together the puzzle. Okay, but really what you're looking at is all of these tiny, tiny little pieces that you have to build into slightly larger chunks that you can then use to build the whole structure. But you have to interpret at each of those stages. Another big thing that you'll notice if you talk to tutors. Tutors that know what they're doing will almost instantly jump to the multiplicity. Why? There's a lot of information stashed in the multiplicity. And so what they can do is interpret that information because they've had experience, and they can do all of the rest of it internalized and jump straight to the multiplicity to interpret. You don't have that experience. Do not jump to the multiplicity. Start simple. If it gets to the point where you just cannot interpret the multiplicity, fine. Accept it. Don't interpret it at all. Interpret everything else based off of your integration, your chemical shift, and the number of signals. You can still solve for the structure with zero understanding of multiplicity. Okay?
You can solve for the structure, I guess what does that do?
Well, what is the goal of all spectroscopy? To identify the structure of the compound. So depending on what tools you want to use, you may go through and identify the compound based off the fragmentation pattern of mass spec. Perfectly valid. If you can go through and do that, kudos for you. Teach me at some point. Just not this semester. Right. If you can solve for the structure of the compound using just the carbon NMR, great. You probably can't, but great. Right. With HNMR, you've got all of those little kind of nitpicky little pieces that can come out of it. And the question is, how do we put that all together to get to a final structure? And that requires a lot of individual steps and breaking it down in each of those individual parts. Okay? So there's a couple things that we'll address first. The number of signals. Okay? So when we're looking at unique carbons, one of the things that kind of worked for me when I was learning this is that if we built a model of the structure, okay, picked it up or pointed to an atom, and then picked up that model, tossed it up in the air, let it fall around, move around, do all sorts of stuff, closed your eyes, all that fun stuff. If you could point to that exact same atom again, with no error, that is a chemically unique atom. There's nothing else like it. If you get it confused for another atom, then those two atoms are chemically identical, and they have the same chemical shift, the same signal. Okay? That's kind of hard to do, particularly if you're going from the spectra to the compounds. You don't have the compound to pick up and toss around. Okay? But that's kind of the idea, is we're building from that. So what can we see? There are some extra terms that come out of this that I always hate talking about and always confuse me, because if you just focus on the structure, you don't need to understand what's going on with these terms. You'll hear enantiotopic, diastereotopic, and theoretically homotopic as well. Okay. What they're in reference to is what happens when you exchange an atom, a hydrogen atom, for atom X. Okay. So if I looked at this structure, and we've got two hydrogens here, one's wedged and one's dashed. If I go through and now make that atom X, and I draw the mirror image of it, whoops. What is the relationship between these two structures? They're enantiomers. What we've got are they enantiomers? Did I draw that right? I did draw that right. They are enantiomers of each other. What we have is signals that we would refer to as enantiotopic. Oh, no, never mind. I remember. This technique is just dumb. We saw it with the other one. Now our relationship between these. So what we do is we take our atom X, and what we're doing is trying to see the relationship between these two structures. So what I did is exchange the location. They're diastereomers, which makes the relationship between the hydrogens that I swapped out for X diastereotopic. What does that mean? They are unique hydrogens, which means I expect different signals or unique signals. Why has that become problematic? As soon as you have a chiral atom, this structure that looks like it may have 4 different types of hydrogen jumps to having more types of hydrogen. This effect is such a nuanced, small effect that it is very rarely shows up outside of trying to mess with students' heads and saying, what's the relationship between these atoms? Okay. Officially, it does show up in the homework, I think, as far as enantiotopic and diastereotopic. Follow the rules of what the textbook is asking you to go through and do to do that labeling. Okay? Really not a big deal. What this is in reference to is when we said that you guys were a detector, and I was facing you, said, you draw me, and if I turned around, you draw something slightly different. That's what this is referring to. So this effect gets minimized by allowing our sample to freely move, and we don't end up seeing it in the spectrum. We see it in a theoretical type question of trying to mess with student heads. Okay? So homework, not exam. I want to make sure you're aware of those terms potentially popping up. Chemical shift, this is a big one. Okay, you all know your nomenclature of esters, right? Is that a yes? Some people are actually saying yes. Okay. I didn't think you actually knew. I was pretty sure I hadn't assigned anything with this. So let's break this down. Ethyl, what does ethyl mean? 2 carbons. There's 2 carbons. Acetate, what is acetate? It's a long shot. Oops. In blue is our acetate. Anybody notice a problem? What was the typo that I made? What's that? I lost a carbon on my ethyl group. There's my other carbon. What we now have is ethyl acetate. So the acetate is referring to the structure that holds the oxygens. The ethyl is a substituent on it. Based on that information, what can we do with the next one? We have methyl and we have propanoate. Why is that propanoate? How many carbons? 3. There's our prop. There's our methyl. Okay. Formula for both of these is what? Assuming I did this right. Exact same chemical formula. If we broke down now and looked at the chemical shifts, the splitting patterns, multiplicity, all of that. So let's now break that out. Okay. How many hydrogens should show up for that position? 3 hydrogens, because there's 3 hydrogens at that position, right? This one should have. And the last one? Let's do that same logic with the first or the second problem. Anybody coming up with a potential problem? What's the difference between these 2 structures based on the integration?
It's just the oxygen placement.
Just the oxygen placement, but HNMR doesn't tell you that right away, sort of. Maybe it's something to do with the splitting pattern. So let's take a quick look at our splitting pattern. So our splitting pattern, when we're looking at multiplicity, there's a couple things we need to take into consideration that says plicity. We have a 3-bond rule, okay, which I'm going to put in quotes because it's not really 3 bonds. Usually less than or equal to 3 bonds qualifies as a neighbor. Neighbors plus 1 equals the number of peaks we see. So if we go back to our problem up here, add a little bit more detail in this. For the first signal on the left, how many neighbors does that hydrogen see? Why 2? We count out our bonds. Ready? 1, 2, 3 bonds. What atom am I at? Hydrogen. Okay, so I agree. There's 1 neighbor. 1, 2, 3. I'm at another hydrogen, so there's another neighbor. 1, 2, 3. I'm at an oxygen. That doesn't count. They have to be hydrogen neighbors. 1, 2. Isn't that hydrogen within 3 bonds? Does not count as a neighbor because it's chemically the same. If it's chemically the same, we could call it living in the same house. We don't qualify that as a neighbor. So for that first one, we only have 2 neighbors. If we have 2 neighbors, what does that mean for the number of peaks? We get 3 peaks. Next one would have 3 neighbors, which means 4 peaks. Next one. So we're looking now here. It has 0 neighbors, which means 1 peak. Move to the other side, what are we going to notice? Not no peaks, no neighbors. It's okay. It's easy to make. Is that problematic?
Same.
It's the exact same splitting pattern. Right? So according to HNMR, we might say, oh, we can't tell the difference between these. Both of these are valid answers. Fortunately, that's not quite true. Okay? We'd get the same number of signals, 3 signals, same integration, same multiplicity. What's the 4th thing? Chemical shift. Right? If you have a lot of electrons around you, you're now shielded. If you have very few electrons around you, what happens? You're de-shielded, so you shift to bigger frequencies. What would potentially cause electrons to not be around an atom? Someone said the atom, but I want a little more detail on that. Electronegativity. Oxygen is very, very electronegative, which means it does what to the electrons in our carbon-oxygen bond? Steals them away. Well, if carbon loses its electrons, what does it do to the electrons in the carbon-hydrogen bond? Takes them away. How many electrons end up around that hydrogen? Relatively very few. Okay? If it doesn't have a lot of electrons shielding it, it becomes de-shielded and it shifts to large chemical shift values. So we'd shift up in that 4 or 5 range. Okay? So we would expect that signal to show up maybe at 4 parts per million. What happens with our other chemical shifts? Well, the very first one on the left, we've got a carbon bound to a carbon. Well, there's not much of an electronegativity difference there, so we expect to see not much shift at all. How about the last one in that molecule? That's a carbon bound to? That's a carbon bound to a carbon bound to 2 oxygens. So we might expect a shift there, but would we expect as much of a shift as we saw for the middle one? No, because it's still carbon to carbon, not carbon to oxygen. So we might put this one as our middle signal, for lack of a better description. What happens to the structure on the left? I mean the right. Thank you for the what, though next time a little louder maybe. Structure on the right. The very first carbon is bound to how many oxygens? 1 oxygen, which means this is going to be a large shift. What happens to the other 2? Not really shifted. We might expect that first one there to be shifted a little bit further than the first one because it's bound to an sp2 carbon. Okay, but we're not seeing much of a shift. How does this help us out? Well, looking at the spectra, what do we expect to see? If we expect the compound on the left, the CH2 signal should be the furthest downfield. If we have the ester on the right, our CH3 signal is the furthest downfield. So we end up interpreting our chemical shifts to decide the structure of our ester. Very, very, very tricky. Also, in my opinion, unfortunately, super, super common on the ACS test. Okay? So I will continue to give you practice with distinguishing between those esters, and it all comes back to chemical shifts. Okay? So you have to be careful with that analysis. Those of you that have done practice with this may realize that once you've got all your pieces together, you may find there's 2 or 3 ways you could have arranged those pieces. Esters, there's always at least 2. And there is no evidence to tell you otherwise until you look at the chemical shifts. In the other situations, you usually have something else to help you piece it out. Okay? Here, it's only the chemical shift. Yes?
Why don't you look at the carbon instead of orange?
I was referencing hydrogen NMR. Are there any hydrogens on that carbon? No. That's why. Okay. If we shifted to carbon NMR, we would see a signal for that carbon. It would show up at 200. Would that be different between the two spectra? No. They'd be pretty much the same. Okay. I don't remember how many more slides we got in this. Splitting of splitting. This is a super complex variation off of multiplicity. So if you don't like multiplicity, this is probably not one you want to listen to. If you're fairly confident with what you have, your understanding of multiplicity, then feel free to go ahead and listen. Okay. What we're looking at in this structure, or in the cases of splitting, is that we have neighbors that are drastically different from each other. So what do I mean by that? If we looked at this structure, we might go through and say that we had, whoops, that's a hydrogen, 4 different types of hydrogen within this. And we might be happy with that, accept that. However, is our red hydrogen and our orange hydrogen actually chemically identical to each other, or are they chemically identical? If we look across that bond, the orange hydrogen sees chlorine wedged. What does the red hydrogen see? It sees the dashed hydrogen. Those two hydrogens are technically different from each other. So that if we now try to go through and look at our multiplicity, which had to do with dealing with how many neighbors we've got, we run into kind of an issue. The red hydrogen is different from the orange hydrogen. So how many neighbors does the orange hydrogen have? Let's not do that quite yet. We've got one neighbor. So we're going 1, 2, 3. Then we can go 1, 2, technically 3 out to those hydrogens, and we've got 3 neighbors out there. What's the other issue? The hydrogen right next to it is technically chemically different. So that's another 1 hydrogen neighbor. So how does this affect our splitting of splitting? So what we're going to do is start with our original signal. We'll assume no splitting patterns, no multiplicity. Okay. So if we take no multiplicity for our hydrogen, we would expect to see 1 signal. So there's our signal. Now what happens if we say that we can see this hydrogen? Well, it has 1 neighbor, right? So what happens to the signal? Splits into 2 peaks. Now let's say we see this hydrogen. How many neighbors do we have? How many neighbors at that position? We've already taken into consideration the red hydrogen arrow. Okay, that one's out of the picture. Now the only one I'm looking at is this hydrogen. There is only 1 hydrogen. What happens to our signal if we have 1 neighbor? Splits into 2 peaks. But what signal are we splitting? We're splitting one that is already split into 2 peaks. What's the result? 4 peaks. Because our signal has already been split, we now have to split the new signal. The new signal is already 2 peaks, so we have to split it. What happens when we now bring in the next neighbor? How many neighbors are there? 3. But if we have 3 neighbors, how many peaks do we need? 4. So we now have to split our signal into 4 peaks. matching the patterns for multiplicity whoops, that's not an I. So every time we have a new neighbor, we have to split the signal. Most commonly, what ends up happening is that the differences between those, okay, the splittings between those effects start to overlap. And more commonly, what we would expect to see in this situation is that when we try to split those two, that they overlapped a little bit. And really what we end up seeing is something along these lines. Because remember, your peaks can add. And that potentially happens on the other side. But then those theoretically overlap. So the net result is that we end up seeing something that we might have predicted from the very beginning. For that hydrogen, how many neighbors do we have? 4, so we would have expected 5 peaks. Those 5 peaks are due to our uber complex splitting pattern that is now added and condensed on top of each other to result in the net result of only seeing 5 peaks. When you see splitting of splitting, or technically even splitting of splitting of splitting, okay, is because we have drastically different hydrogens. If those hydrogens are different enough, they now all split the signal independent of each other. The only time they split identically is when they are identical. But if they're different, they all split independent. Okay? And that gets you in this situation where you can get splitting of splitting of splitting of splitting. The other thing that happens, to detect that difference, we have to get a large separation between each of the peaks. How do we get a large separation between those peaks? You use a stupidly strong magnet. What if your magnet isn't very strong? They all overlap and we don't see the splitting pattern. So this pattern is always, always, always present. We just don't see it because we aren't using a strong enough magnet to be able to detect that difference. Okay? The other one that could potentially pop up is this long distance splitting. Okay? We can sometimes get splitting 3 bonds away plus a pi bond. Okay, so if we drew in a double bond, one, 2, 3, I'm at a carbon, we don't see anything. 4, 5, we could get potentially 5 bonds away, that might see it. Okay? I actually miscounted. That was supposed to be a hydrogen. Okay? So under this circumstance, we're 1, 2, 3 bonds away, we would say there's no splitting. In some very rare circumstances, you do see that splitting up to 4 bonds away. Okay? Again, the stronger the magnet, the better we can resolve it. If our magnet's weak, we can't resolve it. Look at A, B, and C, those spectra. I believe it's A in the spectra packet will actually show you this effect, splitting of splitting, okay, in the long distance version of it. Okay, so if you look at the peaks in the aromatic range, you'll see that instead of just being a nice single sharp peak, or even 2 peaks that resolve all the way to the baseline, you see kind of a fork up at the top. That's due to the splitting of splitting because the magnet that we used to run that sample was really strong.
It says 3 sigma and a pi. Is it always going to be, if you get 3 sigma, it's going to be because there's a pi, doesn't it?
If you're seeing long distance splitting, it's almost always due to a pi bond being involved. Yeah. I can't say always. Always is a bad word in organic.
Regression test.
No. Last thing that I want to address here is a coupled constant. So these things are neighbors of each other, so it causes them to split. Okay, hydrogens that are split will split the other neighbor as well, or split back. So what we can do is look at the difference or the distance between those peaks. That is what's known as the coupling constant, because it is constant for an individual set of neighbors. So if we go through and look at this spectrum, you'll notice that the 2 signals that we see up in the aromatic range, how do you know it's the aromatic range? 6 to 8, you memorize that table that I told you to go through and memorize, okay, in the videos. Those aromatic signals are showing a coupling of 8.5 hertz. If we go through and look at the signals in the alkane-ish range, the distance between the peaks is 7.6. What does that mean? The hydrogens in the alkane region do not see the hydrogens in the aromatic region. Okay? They are not coupled to each other, which means they are not neighbors. But if we look at our alkane region, it's a 7.6 and a 7.6. What does that mean? Those two signals are neighbors to each other. So the signal that makes the one at 1 couples to the one at 2. I still got 2 minutes. Okay. Very nuanced effect. It really comes into play when you're looking at double bonds, particularly cis and trans double bonds. Where's my cis and trans? Oh, there we go. Our cis versus our trans double bond. There is one question on the homework that is going to ask you to go through and do that. One of the things that's problematic with that, what are the units of your coupling constant?
Hertz.
Hertz. What's the unit on your x-axis on the NMR? ppm, not hertz. So you have to do a conversion between ppm to hertz. How do you do that conversion? You need to know the strength of the magnet that was used to generate that. Okay? There's some big stupid calculation that's in your textbook. Again, I don't expect you to go through and do that calculation, okay, for the test. For your homework, I do expect you to go through and do that. Okay?